Next, we consider the maximum leaf spanning tree problem. So a spanning tree is a beloved polynomial time solvable problem, but many variants turn out to be NP-complete. Here we are looking at one such variant. So of course a leaf of a tree is a vertex with degree 1, and a spanning tree of a graph is a subgraph of the graph that is a tree, and it has cardinality of v many vertices. So it is able to reach every vertex of the graph, and so it's a connected acyclic subgraph that is able to reach every vertex. Okay, in the maximum leaf spanning tree problem, the input is a connected graph G, an integer k, the parameter is k, and the question is whether G has a spanning tree with at least k leaves. So as an example, if this is our graph, and we want to know whether this is a spanning tree with at least, let's say, 4 leaves, then what subgraph can we choose? Well, we can add this edge, this edge, this edge, this one, and this one. So now, so in the red graph we have 4 leaves. We're able to reach every vertex, and so this is a connected acyclic subgraph that has 4 leaves. So the first property we're going to use is that if we are able to compute a subtree that has k leaves, that doesn't necessarily span the whole graph, this will actually be sufficient. So we say that a k-leaf tree in a graph is a subgraph that is a tree with at least k leaves, but it's not necessarily spanning. And of course, a k-leaf spanning tree is a k-leaf tree that spans the whole graph, so that reaches every vertex. Now, if we have a connected graph, then I claim that G, so this connected graph G, has a k-leaf tree if and only if it has a k-leaf spanning tree. To prove this, let's start with the reverse direction, because it's really simple. So if G has a spanning tree with k leaves, then G has a subtree with k leaves. That one is obvious, because the same tree just works. Okay, on the other hand, if all we have is a k-leaf tree that doesn't yet reach all the vertices, we're going to try and transform it in a way so that it does reach all the vertices. And we can do this by induction. So suppose we have a k-leaf tree in G, and so currently there's still x vertices that it hasn't reached yet. So the number of vertices it hasn't reached yet is v, the cardinality of v minus the cardinality of the vertices in the tree. So that's our x, and we will use induction on x. And so we will show that this tree T can be extended to a k-leaf spanning tree. So as a base case, we have that x equals 0. So there's no vertex that we haven't reached yet. So in that case, our k-leaf tree is a k-leaf spanning tree, and we are done. Now, if x is larger than 0, so we still need to reach some vertices, and we assume that the claim is true for all x prime that's less than x. So as soon as basically we can reach one more vertex, we are happy, because then we can use induction to then reach all the vertices. So what we're going to do is we choose one vertex, we're choosing one edge such that one endpoint is in the tree and the other endpoint is not in the tree. Okay, now we take our tree, our k-leaf tree, and all we do is we add this edge. So what happened to, so now we reach one more vertex, that's clear. So x decreases by 1. What happens to the number of leaves? So the number of leaves, so this new vertex that we added is a leaf now. and we attach it to one vertex, and maybe that one vertex stops being a leaf, or it wasn't a leaf to begin with. But in any case, the number of leaves does not decrease because, well, the only two vertices that could change their status is, well, the new vertex we add, it becomes a leaf, and the vertex we attach it to, and that one might stop being a leaf. So this new tree has at least k leaves, and it has less than x external vertices. So, and since we assume that the induction hypothesis holds for all x prime that are smaller than x, we can use it to extend our k-leaf spanning tree, to extend this particular tree to a k-leaf spanning tree by induction. Okay, so basically this means as soon as we have computed a tree with k leaves, we can always extend it to a spanning tree without decreasing the number of leaves. Of course, we need that our graph is connected for this to work. Okay, how does this branching algorithm work? So what's the branching strategy that we use? So first of all, the algorithm will check whether G has a k-leaf tree. If so, we know that it has a k-leaf spanning tree. Now, the algorithm will build this tree, and it needs some place to start. So let's say it starts at some internal vertex of the tree. And we know that a tree with at least 3 vertices has at least one internal vertex. Now, for this initial vertex, this initial internal vertex, it guesses a vertex R, which means that, well, it considers each vertex of the graph as this initial vertex, this initial internal vertex of this k-leaf tree. It does this only once, so this will contribute a linear factor in n on the running time. So now assume that in any branch that it's considering, the algorithm has already computed a tree, a subtree of G. So this tree has a set of internal vertices I that contains this special vertex R. And then it has a set of leaves. And so the set of leaves, so a leaf of this tree T has one of two types. So either it's a branching node, so it's in the boundary set here, or we have already decided that this will be a leaf of the final k-leaf tree that we are computing. If it's a branching node, then we can still extend the tree from this branching node. So we can still extend the tree at the branching nodes, but for the leaves, we have decided that they are leaves of our k-leaf tree. And then we have all the other vertices. Those are our external vertices. Let's look at the picture. So in blue, we have the tree T that has already been computed. It has a set of internal vertices, and R is one of these internal vertices. And then the set of leaves is partitioned into two. So we have the set L, and we are not allowed to add any more edges to the tree that start from L. But we will extend the tree at the vertices in B to reach some of the external vertices, like this. Okay, so that's our setup, and now the question is whether this tree T can be extended into a k-leaf tree where all the vertices in L remain leaves. Okay. So we can start with our simplification rules, or the halting rules first. So if this blue tree here has already k leaves, then we are done. So if the size of B plus the size of L is at least k, then we can stop and we can return yes. otherwise if the previous rule did not apply and the number of branching nodes is 0, then we will not be able to extend the tree. So we are stuck. We don't have enough leaves yet. We are not allowed to add any more or to extend the tree anymore. So we have to return no. If there's a branching node that has no neighbor in the set X, so no external neighbor, so in a branching node, well, a node is in the branching node, a vertex is in the set of branching nodes because, well, we could potentially extend it and extend the tree at this branching node. But, well, if it has no neighbor in X, then we can't do it, and we will move the vertex into L. Okay? Now, what's our next rule? The next rule is our branching lemma. So it's not yet a branching rule, it is a rule, it is a lemma that our branching rule will be based on. So suppose we have a vertex in B, so branching node, and we have a yes instance. So in particular, there exists a k-leaf tree T prime that extends T where U is an internal vertex. So if we have a vertex in B, so usually we consider two options. So either we say that U becomes a leaf, or it remains a leaf, in which case we move it into L, or we somehow extend the tree at U. So if we decide to extend the tree at U, so U becomes an internal vertex, then this branching lemma says that there exists a k-leaf tree, T double prime, that extends the tree that is obtained from T by adding now all the edges where one endpoint is U, so this branching node, and the other endpoint is a neighbor of U among the external vertices. So this means now that, well, if we look at all the neighbors of U that are in the set X, then, so this branching lemma says that, well, either U becomes a leaf, or we can add all of these edges into the spanning tree. So not just one of them or two of them, but all of them can be added into the spanning tree. So if the tree can be extended at U, so if there's a tree that extends T with at least k leaves and U becomes internal, then there's also such a tree where U is internal and we add all of these edges. So why is that the case? So we start from T prime. So T prime might not contain all of these edges. So maybe it just contains two of them and then there's one missing one. So we start from this one. And now we check what happens if we actually add this edge. Well, if we add this edge, either we get one more leaf, in which case we're happy, or, well, it could be the case that, well, this vertex was somehow already in the k-leaf tree, and we create a cycle. Well, in that case, we need to delete one edge now. So what would be a smart choice? Which edge should we delete? Could have multiple incident edges as well in the spanning tree. Okay, so we added this edge UV. Okay, but we created a cycle, so we have to basically delete one edge of this cycle. And so what we can do is just delete the next edge on this cycle. So let's say we decide that, well, this edge now will not be in our spanning tree anymore, in our tree anymore. Okay, so we start from T prime, and so for every edge that's a neighbor of u and that's among the external vertices, so if this edge was not yet in the tree, then we add it, and we add the edge uv. Otherwise, well, we also add the edge uv. This creates a cycle, and we remove the other edge of the cycle that's incident to v. So what happens to the number of leaves? So I claim that this does not decrease the number of leaves. So what changes? So u was not a leaf to start with. We said that u is internal. So after doing this modification, u stays internal. Okay, so if v was a leaf before we started, so this means that, well, only one edge was incident to v. Only one edge of the tree was incident to v. But now what we did to v is we added one incident edge and we removed one incident edge. So if v was a leaf to start with, it stays a leaf. Okay, and then the only other vertex that we affect is, well, this other vertex here. And all we did to it is we removed one incident edge. So it can't be the case that it was a leaf before and it's not a leaf anymore because we removed one incident edge. Okay, so, and that's all the changes. So that's all the statuses that can change between being a leaf and not being a leaf. Yeah, so it increases the number of edges only incident to u, and u was already internal. For every other vertex that's affected, either its number of incident edges remains the same or it decreases. Before looking at the next lemma, let's go back to our drawing board. So, and let's think about what the branching would do. So if we have a vertex u in the set of branching nodes, we will either move it to L, in which case, well, we make some kind of progress because in terms of the number of leaves, because we know that u will be a leaf in the final spanning tree. On the other hand, if u becomes internal, then, well, we saw that we can add all the incident edges that connect u to an external vertex. And so in this example here, well, u was a leaf in our current tree, and now u is not a leaf anymore, but we created 3 new leaves. So we increased the total number of leaves of this tree T. So we also made progress in terms of T, in terms of the number of leaves that we create. So this seems to be very nice. There's one special case that deserves more attention. So, namely when, well, u has only one external neighbor. So now if you say that u becomes internal, so u was a leaf before, u becomes internal, and we create one more leaf. So the number of leaves didn't change. So in this branch, it seems that we wouldn't make any progress. So that's an issue. And so the way to solve this issue is by saying that, well, if u really becomes internal, there must be a good reason for doing this. Because, well, if everything that would result from making u internal would just be one more leaf, we could just make u a leaf instead. So our follow path lemma will say that there must be a situation where at some point we get at least 2 leaves as a result of having made u an internal vertex. And well, this could go on for longer, right? So we could have u has degree 2, and then the neighbor has degree 2, and then its neighbor has degree 2. But at some point, we must be able to increase the number of leaves. Otherwise, just make u a leaf, and that's it. So this is what the follow path lemma does. So suppose u is a branching node. It has one external neighbor that's called v. Now, if there exists a k-leaf spanning tree that extends T where u is internal, but there's no k-leaf tree extending T where u is a leaf, so if we actually have to branch in such a way where we make u internal, then there's a k-leaf spanning tree, a k-leaf tree, that extends T where both u and v are internal. So the only thing that says is that, well, it can't be the case that v becomes now a leaf. And we stop here, because otherwise we might just have made u a leaf. So if u is internal, then v will also become internal, and we can apply the same reasoning to v. So because v is then internal, its neighbor also needs to be internal, etc., until we reach a case where we create at least 2 more leaves. So the proof is just suppose that this is not the case, then we could just make u a leaf. So if u is internal and v is a leaf, then just removing v from the tree gives us a k-leaf tree where u is a leaf. Okay. So our algorithm can now be described as follows. So first of all, we apply all the halting and simplification rules. We select the branching node, and then we consider 2 cases. Either we move the branching node into L, so we remove it from B and add it to L, or we make it an internal node. That means that by the branching lemma, we can now add all the edges that connect U to an external vertex into our tree. In the special case where it has one external neighbor, then we also make this external neighbor internal, and then we recursively do this according to the follow path lemma until we reach a vertex that has at least 2 external neighbors. In the special case where a vertex has no external neighbor, this says that we return no, but actually we don't even need this part of the algorithm because we had a simplification rule for this. So we moved it into L. Okay. So what do we have? So we have that in one branch, a vertex moves from B to L. In the other branch, B increases by at least 1. And we want to argue that in both cases, we make some progress. Measuring this progress is not so easy because, well, if we think of our parameter k stays the same the whole time, right? We don't change k. So we need to measure something else than just k, because, well, we could measure the number of leaves that we get in the end. So we could measure the size of L. So maybe as a measure we could say, okay, how many leaves do we still need to find? So maybe you could use this as a measure. Well, for this measure, this measure decreases when we move a vertex into L. So in the first branch it decreases, but in the second branch it doesn't. So although we create more leaves, this kind of measure doesn't take into account the size of B. So we need something slightly different. And so we will use this measure. So the measure is 2 times k minus 2 times L minus the size of B. Okay, so what we have is that this measure is always between 0 and 2k, because, well, if it's less than 0, then we know that the number of leaves that we currently have in our tree is at least k. So then we would have stopped. And initially this measure is at most 2k, and it can never increase because we increase the size of L and B, and the measure can never increase. Now, in the branch where we add U to L, we have that B decreases by 1 and L increases by 1. So in the measure here we have minus 2 times the size of L, but only minus 1's the size of B. So in total, when B decreases by 1 and L increases by 1, we have that the measure mu decreases by 1. Okay, let's consider the other branch. If we make U an internal node, so we know that by the follow path lemma at some point, 2 vertices get added to B. So one vertex disappears from B, that's U, and at least 2 new vertices move from X to B. So B increases by at least 1. Nothing happens to L, nothing happens to K, so we have that mu decreases by at least 1. So we have that in each branch, mu, this measure mu, now decreases by 1, and so that means the height of our search tree is at most mu, because we start off with mu, and so each time mu decreases by 1, and when it's 0, we stop. So the height of this binary search tree is at most 2k, because mu is at most 2k. And the search tree is binary because in each branching step we make a branching into 2 cases. So I have a binary search tree with height at most 2k, so that gives us then at most 2 to the power 2k leaves in our search tree. So our running time in the end will be O star of 2 to the power 2k. So that's the same as saying O star of 4 to the power k. So this was proved by Kneis, Langer, and Rosmanit in 2011. And the result is that maximum leaf spanning tree can be solved in time O star of 4 to the power k. And this is exactly the algorithm. Okay, if you want to read more about search trees, branching algorithms, there's a few chapters in our textbooks, and these are the references.